Hello everybody, the purpose of today's video is to summarize some of the important concepts related to curve sketching. So this is all stuff we talked about before, so I'm going to go kind of quickly through this. Just stop and pause and reflect the video anytime you don't understand what I said, and rewind it if you need to. But the first case, we're given a function, and this is f of x, and the graph in the information tells us that we have stationary points when x is -3, and when x is 2, and when x is 0. And what they ask us to do is write down the x-intercepts of the graph of the derivative. Well, here's where we have to just basically know what our definitions are. In order to have a local maximum or minimum, we have to have a derivative equal to 0, a stationary point, if you will. And when the first derivative is equal to 0, that amounts to an x-intercept of the derivative function. So all I have to do is state the x values for all three of my stationary points, and those are the x-intercepts of the first derivative. So basically the whole point of exercise 1A is to identify that stationary points exist where the derivative crosses the x-axis. Next, we're asking for when is the first derivative positive. The first derivative is positive when the function is increasing. So if the function is going uphill, then our derivative will be above the x-axis. So anytime the function is going uphill, from -3 to 0, or from 2 to 4, then we know that the first derivative is going to be above the x-axis, positive. And finally, it says at point D, the x-coordinate is -1/2, and it asks us to explain why f double prime of x, that's the second derivative, is negative. So at the point D, why is the second derivative going to be negative? All you have to do is look at the graph and say it's concave down, and since the graph is concave down, then the second derivative will be negative. Another way to look at it is the function is increasing at a decreasing rate. So we're going uphill, but we're slowing down as we do. So a negative acceleration. Good, moving on. We have to find the coordinates of the points of inflection on the graph of, and what we have is a cubic polynomial. So I find the first derivative so I can get the rates of change, and then I take the second derivative so I can determine concavity and inflection. So when the second derivative equals 0, we have an inflection point, and that is when x equals 2. So it said coordinates. I have to make sure I'm asking for the coordinates or just the x-coordinate. If it asks for the coordinates, then we put that value back into the original function, and I got y equals -2/3. So first of all, the coordinates of the point I'm looking for are 2, -2/3. Second of all, I just have to verify that there is in fact inflection. That is go from concave down to concave up, or vice versa. So I evaluate the second derivative at x equals 1, which is less than x equals 2, and I find concave down. I evaluate the second derivative at x equals 3, which is more than x equals 2, and I find concave up. So we go from concave down to concave up, which means we have an inflection point at the given 2, -2/3. To verify on the computer, I verify that 2, -2/3 is a point on the graph, but I also look at the concavity. Concave down when x is less than 2, concave up when x is greater than 2, which is confirmed by my analysis. For number 3, we're given a polynomial, and they label 2 points A and B, where A is a maximum and B is a point of inflection. So I should tell myself to find A, I would set f prime of x equal to 0. To find B, I would set f double prime of x equal to 0. And that's what they want us to do, find the coordinates, be the x and y coordinates for the points A and B. So for a maximum, we want the derivative to equal 0, so I take the derivative, set it equal to 0, and that's a factoring problem, so that's fun. This is applying factoring by grouping. At the end of the day, I find out that there are 2 zeros for the derivative, one when x is 1 and one when x is -1/3. It's more likely, since this is a maximum, that we're going to take the negative value for x, so -1/3 should probably be the right one. I should check this, which I will with technology later. But to find the y value, I just put -1/3 into the into the original function, and find that 3 5/27 is the y value that corresponds to -1/3. To find the b value, I take the second derivative and set it equal to 0, and that gives me +1/3. And I evaluate the original function at +1/3, and I get 2 16/27. So that's the coordinate of the inflection point. So that's all good. And again, I would check that with technology for sure. I'm just going to jump ahead here and finish the question. Now that we know what the points A and B are, we're supposed to find the equation of the line that contains both A and B. And so to do that, I need to know the slope of the line. And that requires a little bit of arithmetic. And I get -8/9. And then to get the equation of the line, I just use the point slope formula. So here's the point, 1/3, 2 16/17, and the slope, -8/9. I just put that all into the formula, I solve for y, and that'll be the equation we're looking for. I hope you don't mind, I didn't do that part because it's busy work. We're just getting into the big ideas, like what am I supposed to do? And here it says find the x-coordinate of the points on the line, or on the curve, at which the tangent is parallel to this line. So in other words, we have a line going through A and B whose slope is -8/9. They're saying that there has to be a couple of points on the curve where the slope of the tangent is 8/9. And so to do that, we just have to go to the derivative and find out when is the derivative equal to -8/9. So I put this number in, and I get a quadratic equation. And again, I hope at this point we all know how to solve quadratic equations. This is going to be busy work, but in terms of setting it up for what the question was asking, find the x-coordinate of the points where the tangent is parallel to this line. In other words, I want to know what values of x make the derivative equal to -8/9. And that's the equation I set up and the algebra that follows. On to number 4. This again a straightforward question. Number 4 is asking, well, it's giving us the first derivative, and we have to first find the second derivative. So I'm going to use a shortcut here and get 3 times x minus 3 squared. Remember, that only works if the coefficient on x is 1, and this is a linear expression. Then you can just use the power rule on the outer portion. Otherwise, you'd have to FOIL it all out and then take the derivative, but in this case, we're allowed to apply the shortcut. We have to evaluate now f prime of 3 and f double prime of 3, and when I do, I realize very quickly that both the first and second derivatives are 0. So now what we have to do is actually interpret what does this mean when this is a stationary point and this could represent an inflection point. Is this a stationary inflection point or not? But if I already read the problem and it says the point B or the point P on the graph has x-coordinate 3, we found where x is equal to 3, so explain why P is not a point of inflection. So that's where we have to get a little creative to answer this question. To be inflection, we have to show that on the left side of our special point, the graph is concave down or up, and then the concavity changes as we go past x equals 3. So in other words, we could put together a nice little number line. Or without a number line, we can use our head. Since 2 is less than 3, we evaluate and we find it's concave up. Since 4 is greater than 3, we find that in the second derivative and find it's also concave up. Since the concavity does not change on either side of x equals 3, then we do not have inflection when x equals 3. So this is a warning from the authors of this problem that just because the second derivative equals 0, that does not guarantee you have inflection. And this is the example that they're using to illustrate that fact. All right, part 2 of this video will be forthcoming, but this was getting a little long, so I'm going to stop it now, and we'll pick up the part 2 with exercise number 5.